So we finished last time talking about tools for solving Newton's laws problems. There was a bit that I wanted you guys to make sure that you take a look at that's in the lecture notes and on the LibreText that I didn't go over. It's just another example, but I do suggest you look at it. And so we're going to kind of change gears now. We're going to change gears to talk about work and energy. And by the way, please let me know if my audio/video start acting funny. I can always call in if I need to. Right. So let's talk about work. So for a lot of problems, like just problems that you might want to solve from a physics perspective, you don't really care about like the direction of the velocity. Often you just care about the speed. Like, for example, you might ask, if I, if a roller coaster goes around a series of loops and it goes up and down some hills and it starts off at this speed, how fast is it going at the end? We don't care that it changes directions all throughout the whole way, and we don't care what direction it's going at the end. We just want to know how fast it's going. So in those cases, we really don't need to overcomplicate the problem by handling vectors and by handling forces and accelerations and asking how the vectors not only change direction, but also change speed. And so what we can do is we can actually use a somewhat a method that requires less information, but also outputs less information. So what I mean by that is, to solve Newton's laws, you need all of the information, or to use Newton's laws to solve a problem, you need all of the information about a problem so that you can figure out all of the forces and, figure out the accelerations and then apply kinematics and so on and so forth. But the output of doing that procedure is you get all of the information. You get the velocity, you get the velocity at every moment in time, you get the acceleration and the position at every moment in time. So you get a lot of information out if you put a lot of information in. But because some problems only require, we might only want to know how fast something is going at the end of the day, you don't need to put as much information in. So we don't need to worry about really vectors that much at all, or at least we don't have to work entirely with vectors. So we want to come up with an alternative approach to handle changes in speed. So that's what we're going to do. So we want to probe how the force on an object can affect the magnitude of velocity. And remember, the magnitude of the velocity can be written as vertical bars around the vector. And so what we could do is, or what we're going to do is, we're going to try to effectively ask how the magnitude of the velocity changes with time and see how that relates to various forces and so on. So in principle, we could, it's doing that thing again. In principle, we could just examine, or we could just compute rather, the time derivative of the magnitude, right? That's something that we could just do. And that would be great. It would tell us exactly how the magnitude changes with time. And so maybe we could relate that to the forces. The only trouble is that involves a square root. And generally, like the magnitude of the velocity involves a square root. And so taking the derivative, by probe, I mean like investigate mathematically. And so when you take the derivative of that, you're going to end up with a square root in the denominator, and it will still depend on the velocity in some strange way. So instead, we're going to actually work with a slightly simpler, or what looks like a slightly more complicated expression, but it will actually make the calculations we're about to do easier. So instead, we will characterize how the time derivative of v squared changes. Or not how the time derivative changes. We will characterize how v squared changes, i.e., we will compute the time derivative of v squared. And now the time derivative of v squared, the reason why we do this is because this is just vx squared plus vy squared plus vz squared, right? It doesn't involve any square roots or anything. So the time derivative will be a lot nicer. So this is something that we can handle. And then at the end of the day, once we figure out what the final squared velocity is, we can just take the square root at the end. So let's compute the time derivative of the velocity, right? So this is equal to, by definition, this is the time derivative of the magnitude squared, right? So v squared is often, it's v dot v, but it's the same thing as the magnitude squared. They mean the same thing. And so we can apply the chain rule. Actually, I should have written this in the other way. Let me put the bars there, and let me get rid of the bars here. It'll make a little bit more sense. The order will make more sense. So if v squared without the bars is v dot v, they're both v dot v, but this is just a simpler way to see it. This is the time derivative of v dot v, right? And so now we can use the chain rule, or rather the product rule, they're really the same thing, to get that this is 2v dot ddt of v. Hopefully you guys see how we get there. I'm just doing it to this one and then doing it to that one, but they're the same thing. It's just like doing the derivative with respect to x of x squared. You get 2x, and then here we have dv dt because v varies with time. And we know what dv dt is. That's the acceleration. So the time derivative of v squared is twice the velocity dotted into the acceleration vector. Now this is strange, but so far what this means is it tells us how the acceleration affects the change in the velocity, or rather the change in the square in the velocity. So you might get the idea that we're getting there. So because now we can use the fact that acceleration is related to the force. It's equal to F net divided by mass. And so taking this result, we get that the time derivative of v squared is 2 divided by m F net dot v. So, or put another way, rearranging this, all I'm going to do is multiply and divide both sides by, or multiply both sides by m over 2. Where did the 2v come from? Because you have to take the derivative of this one and that one. You're doing it twice. You have to apply the product rule. And because they're the same thing, you just get 2 factors of the same thing. So then we get that ddt of 1/2 mv squared is equal to F net dot v. So this is a useful result. So this tells us the rate at which this quantity, 1/2 mv squared, changes. And it tells us that rate in terms of the net force that's applied to the object, and it also requires the velocity at that time, which kind of makes sense. Generally, the rate at which something is changing depends on the value of that thing at any given time. That's a reasonable function. Like f of x or f prime of x depends, in a sense, well, obviously it depends on x, but it could also, in principle, depend on f. That's neither here nor there, though. So this is great. It tells us how much 1/2 mv squared changes by, but we don't exactly want that. What we want is we want to know how much v changes by, and not just the rate. We want to actually know like the change in v between two points in time, or between 2 locations. So we want delta v, or rather, what we would like really is we would like delta of 1/2 mv squared. We're not going to be able to get delta v out from this, but what we can do is we can get the change in this thing out, and then once we know the change in that thing, then we can solve for the change in velocity later. So the way that we're going to do that is we're going to integrate. So before we integrate, let's just simplify our expression a little bit. So first, I'm just gonna give a name to the thing that, or to the position vector. So we're going to suppose, this is just a fancy way of saying, assume that v can be written as the time derivative of a vector L dt. So this L, that represents, acceleration is not constant. No, this is fully general. This is for any velocity. So that L, this is this is a position vector. It's just like R, but we use L here because that's traditionally what's used. So that means that dl is a small change in the position vector, or is a small change in the position vector, i.e. it's a small displacement. Sorry, I ran out of room. And dt is a small duration, which is to say that, of course, this is true. This is just the time derivative of the position vector. dl is just a very, very small delta r, and dt is a very, very small delta t. But now we're going to do what you typically can't do in a math class, which is we're going to split the derivative. And so then we're going to say that the time derivative, well, we're about to do this, of 1/2 mv squared, this is f net. We're just substituting that in to our above formula, times dl dt. And now we're just going to multiply both sides by dt. I hate saying that, but that's what we're doing. So we're going to multiply both sides by dt, or just cancel off the dt's. And we get that d, 1/2 mv squared, equals f dot dl. And by the way, this f is the net force everywhere. So dl here is a very, very small displacement. So really, if we wanted to be consistent, we should have used r, because that's what we used at the beginning of the course. But for some reason, the convention that's used for this type of calculation, and people have been doing this type of calculation for 150 years, is they use L. Really, it's because we're going to end up with a line integral, and then L stands for line. So just like, if it helps, just think of L and R as the same thing here. Like they literally are the same thing. Right, okay. So we have this quantity here. We have d of something that is a very, very small change in that thing is equal to a force dotted into a very, very small change in distance, right? So just to be clear here, this is true at a particular place or a particular time, right? This equation holds for all places and all times. The small change, or for all places and all time durations, I suppose, or rather position displacements. For every small change in position, for every small dl, you can figure out how much this quantity, 1/2 mv squared, changes by dotting that dl by the force. So that's true. That's always true. However, dl doesn't have to always be the same thing, right? dl is a small amount of displacement. So you can imagine if an object starts at position A and ends at position B, well, at various points in time, the small displacement vector, let me use a different color. The small displacement vector is going to point in different directions depending on where you are along the path, right? So each one of these is going to be its own dl. And so on. And so what we're doing is, if we want to find the change, if we want to find the small change in 1/2 mv squared between, say, this point on the left and this point on the right, what we would have to do is we'd find the force that's applied at that location, dot it into the dl vector, and that would tell us how much this is changing by. So if we want to find the total amount that 1/2 mv squared changes by between A and B, then we have to integrate. We have to add up all of those small changes that we get as we inch along the path. So I think I covered just about all of that. So the way that we do that formally, and you guys have seen this sort of thing where you add up a bunch of infinitely small things, it's an integral. So we're just going to integrate both sides. So we have an integral from A to B of d of 1/2 mv squared equals an integral from A to B of f dot dl, f net dot dl. So what we're doing is, this is not an integral with respect to time. This is an integral over, oh, and let me actually simplify before I continue. So you guys know that if you do an integral of d something, it just spits out the something at position. This is just something b minus something a, right? It's just like if it was dx from 0 to 1, it would be 1 minus 0, right? So this is just to say that the left-hand side can be simplified fairly easily. It's just 1/2 mvb squared minus 1/2 mva squared. And so this is what we were aiming for, by the way. We get an equation for this thing, And then if we know VA, then we can solve for VB. That's why we were headed this way the whole time. And then this is equal to an integral from A to B. We're integrating along a path. We're adding up those little path lengths dotted into that force vector as we inch along the path. F net dot dl. So now we have to kind of talk about what this means. So this is a kind of an involved procedure, but this is just a number. This is just like this integral that we did. This is it's not a time integral. We got rid of the time integral by multiplying both sides by dt. We made it into a position integral. We're integrating from an initial position to a final position. Now, there's a difference between just integrating from point A to point B and then going in a straight line and integrating in a wiggly line, right? There could potentially be a difference if you went that or some other path or whatever, right? Because if the force is different at different places, for example, on a spring, the force is different depending on how far away you are from equilibrium, the path that you take to go from A to B might matter. So this is not just F net dx, right? In some straight line sense. This is what's known as a path integral, or sorry, not a path integral, a line integral. And so the line that we're talking about is the line is the path. It's the path that the object takes as it goes from A to B. And the path that it's taking, that it takes is described by this path length vector, dl. So this dl tells us at a given place, how much or what direction do you inch forward in to go to the next place? And then at the new place, how much forward or what direction do you inch forward in to go to the next place, and so on. So this dl is going to be changing depending on the direction of the path. It'll point along the path in general. So what we're doing here is we're taking the force at one point. Let me draw a new picture. Let's say the object is going again from A to B. F can change. It doesn't have to, but it can. Let's say that the force is here, and then it's here, and then it's here, and then it's here, and then it's here, right? So if we wanted to approximate this integral, what we would do is we would, let me use red for the path length integral. So we would have two vectors at any given point. We would take their dot product and then add up along the path. And that would be an approximation of what we're doing. Right, this would be the equivalent of like a Riemann sum, but for a path length. And so you just do the dot product for these two vectors, then for these two vectors, these two vectors, these two vectors, and these two vectors, and add up your answer, and that would tell you what 1/2 mv squared, or the change in 1/2 mv squared is. But we do want to do this infinitesimally, so it's not just an approximation, and doing so requires doing a path integral, not a path integral. I need to stop saying that. A line integral. What that boils down to doing, the black arrows represent force, and the red arrows are dl. Sorry, yeah. So what we end up doing is we want to describe this path in terms of some parameter. Like, for example, if this path was in the xy plane, we did a dot product because that dot product was there all the way from the beginning. That dot product is that dot product. The dot product never left. That's why it's still there. Because because v squared is just the dot product of v with itself. So the way that we handle these integrals, the way that we actually turn them into integrals that we can just do mathematically, the way that you guys know how to do them, is we just parameterize the path. We say, look, this object is at position x and position y, and that position y depends on the position x, right? So you could actually describe the path with a function. You would describe it as x, f of x, right? For every point x, there'd be a point y. Now, sometimes that's not true. Sometimes, like, your path is a circle, in which case you'd have to break it up into two paths and then add up the integral. But for the simplest paths, you can describe a path with a function. Yeah, I wouldn't parameterize it with t. Maybe parameterize it with L if you want, but generally you can even parameterize it with x or parameterize it with y. And then, well, dl is just going to be the amount that you move over in the x direction plus the amount that you move over in the y direction. So this would be dx in the I hat direction. And then how big is dy? dy is just the dy can be written using the chain rule as dy dx dx. Yeah, insert any dummy variable, but it'll be easiest to use x. So we'll often write dxi plus f prime of x dx j hat. So basically what this does is it lets us define our integral in terms of just one variable, x. And then we can just integrate from the initial x, say xa, to the final x, say xb. And so then our integral would become xa to xb. By the way, this is kind of off the cuff. There's a good summary of path integrals. I keep saying path integrals. Path integrals are a thing in physics. There's a good summary of line integrals in the LibreText, which I highly recommend you take a look at. It'll be super useful because this is tricky for a lot of you. Not a lot of you have seen this before. So what this does is dl, which became this thing, becomes now it's fnet dotted into 1, or rather I hat plus f prime of x j hat dx. And now you just need to describe the force in terms of the parameter x, and then this is just a number in terms of x, and then you just do an integral. From there, it's just doing the integral that you know how to do. You just have to figure out what the net force is, write it out in terms of components, write out all of its, like maybe if it depends on the vertical position, you would have to use the substitution that y is equal to f of x. It would take a little bit of work, but it does just become an integral in terms of the position x, and that's the way that you would do that. In a lot of cases, this is a lot easier than it seems. I'm just showing you the general way because it seems improper to not show you how to do it generally. We can talk about this in more detail after lecture if you'd like. There's a really good summary in the LibreText. Once again, you should look at it after lecture, but I'm going to continue from here. Right. So that's how you handle this line integral. Oops. So this is just a number. It spits out a number, right? And then you'll know that 1/2 mvb squared minus 1/2 mva squared is equal to a number. And then you could, if you knew, say, the initial velocity at position A, then you could solve for the final velocity at position B. So, oops, scroll please. Right. So I'm gonna write down the final equation that we ended up with again. So this is what the equation looked like. By the way, the method that I used to do the line integral above, maybe it doesn't always work. Maybe you can't parameterize in terms of x because maybe it loops back on itself a bunch of times. Then maybe you parameterize in terms of y, and then you would write the position as f of y, right? It doesn't matter which variable. You could parameterize in terms of any variable that you want, but you do have to parameterize in terms of a variable. That's important. Right. So this is the equation that we had. So this thing, I started off this section calling this section work. This thing is given the letter W, stands for work. This thing, this difference, we call this delta KE. So what does delta KE stand for? Well, delta KE, the delta, as with most things, indicates change, and the KE is in kinetic energy. Right, so kinetic energy is the thing that's described by 1/2 mv squared. So this KE stands for kinetic energy, and kinetic energy is just 1/2 mv squared. And what it tells us, what this formula tells us, and by the way, this formula is assuming that there's no rotational motion. This formula is just a true formula about forces and velocities and masses. It's just true about our universe. So it tells us that this thing, this combination of velocity and mass and the number 1/2, changes in a very special way. And the amount it changes by is given by something that you can compute in terms of work. So What that means is if there's no net forces, if the net force is always 0, then the change in kinetic energy is always 0, which is just another way of saying that this is a thing that stays the same unless you do something to it. This is what's known as like a conservation law, and we'll get to that later. I just wanted to give you a taste. W stands for work, and in particular, it stands for work done from A to B. So that is a force or multiple forces do work on the object. So work is like a change in something. It's a change, it's some physical thing that happens and changes to the object, and it takes place between two places. So when you're pushing a block, you are doing work from where you started to where you end. And that work that you're applying changes the kinetic energy of that block. So we can simplify this equation using this new language. We get that very, very simply, we get that the change in kinetic energy is equal to the work done from A to B. This is how we'll often write it. We'll say the work, and then the first thing is where it starts, and the second thing is where it ends. So this is what's known as the work energy theorem. So I'm going to write down the work energy theorem, and I'm going to write some words. I'm going to rewrite the formula that we've been writing, and I'm going to put it all in a box so you have it all in one place. This is a big deal. Work energy theorem is kind of the backbone of mechanics. So the work energy theorem mathematically can be written as 1/2 mvb squared minus 1/2 mva squared equals a line integral from A to B of the net force dotted into the path length vector. In words, we have that the total work done, I say total because you can actually compute the work done by an individual force and then add up all of those to get the total work. So the total work done by all of the forces, acting on an object from a starting to an ending place, a starting point to an ending point, that starting point being A, that ending point being B. By the way, these are points in space, not points in time, equals the object's change in kinetic energy between those two same places. All right, that's a lot of writing, but that is a statement of the work energy theorem in words. And we now know how to compute the kinetic energy, and in particular, we can figure out, if we know the change in kinetic energy, then we can find the change in velocity, or rather, if we know the initial kinetic energy and the change in kinetic energy, then we can find the final kinetic energy, and therefore we can find the final speed. That's why this is useful. Now, just as a quick aside, maybe it's not an aside, it's actually a useful statement. So in this equation, this is in the equation that is the work energy theorem, the one that's inside the box. Only part of F net contributes at any one place. Right? That's important to note. I say that any one place because, or I say that only one part contributes because if, say, the path vector at one particular location is just in the x direction, it doesn't matter how much of the force is in the y direction because the dot product only cares about the force in the x direction. This is that example that I alluded to on the second lecture of the quarter, where we said that the work is related to F dot dl, or rather F dot L, really. In that which is true when the force is constant. So here, what we see is that that the force doesn't care about the part that's perpendicular to the path. So this is why the dot product is useful, because we observe in reality that if you're pushing on something down a lot and also a little bit forward, the only part that actually moves it forward is the part of your force that is in the forward direction, and that's captured by this dot product. So just to summarize, well, I guess I just did summarize. So super useful. That's a useful fact because it means that sometimes we won't have to care about forces that are always perpendicular to the path. And we'll see an example of that in a little bit. So let's just talk about units really quick. So everything that we've talked about up until now has had units. There's like newtons are the units of force, but now we have this new thing called kinetic energy. And so we can figure out and work. So we can figure out the units of that too. So the units here, so kinetic energy can be written as 1/2 mv squared. Mass has units of kilograms. Velocity has units of meters per second. So this is meters per second squared. So kinetic energy has units of kilograms times meters squared per second squared. That gets a name too. We get joules, which is abbreviated by a capital J. Again, named after like a guy in the 1700s. There were a lot of Europeans in the 1700s who had stuff named after them. It's just the way it is, something imperialism. And so from the work energy theorem, we actually find that because the left-hand side is joules, the right-hand side also has to be joules. So we find that the units of work is also joules. 19th century? Okay, you're right. I thought it was 18th century. I could be off in my timeline though. Right, so again, I just want to be very, very adamant that you guys should check out the examples and check out the details on doing line integrals in section 3.1 in the LibreText. I also linked to a few examples that you guys should work through just so you guys can get practice with this, because this is it's gonna take some time to get this down. You guys should definitely put in practice. I would like to do at least, oh God, we're only 2 pages in. Oh God. Okay, we're 2 pages in, we're 32 minutes in, not looking good. Let's talk about pushing a block. So, yeah, let's talk about pushing a block. Yeah, let's just work through a quick example so you guys can see how this actually plays out. Pushing a block at an angle across a rough surface. Right. Okay, so the picture here is you have a block sitting on a rough surface. You start off at, say, position A, you end up at position B. You're pushing it, say, this way with some angle theta. Let me put that a little bit closer to the ground. The ground is really rough, scraggly, so there's going to be friction too. And you want to just push it you want to just push it at some fixed whatever, like if you're just pushing it, some fixed force, applying some fixed force F down and to the right, and it's moving with some speed V. We're going to assume that F is constant here. This distance we will call delta X, and we want to figure out the force done. Sorry, we want to figure out the work done from A to B. So let's first find the net force, because if we want to compute the work being the right-hand side, we need to figure out what the net force is and then do an integral. So to do the net force, it's relatively easy. It's a rough surface. So here's our, actually, I'll just draw a block. We do our free body diagram. We know that there's a normal force pointing up. There's a gravitational force pointing down. There's a frictional a kinetic frictional force pointing left. We're assuming it's already moving at some speed v. And then there's a extra force F pointing down at an angle theta, right? Okay, standard free body diagram. So the net force vector is, we're going to use the standard coordinate system, x and y. So in the I hat direction, we have F cosine of theta, do some trig there, minus F sub k. the I hat direction plus n minus fg in the j hat direction. Okay, now what about the path? So there are two parts of the path integral, the line integral. There's the force, and then you need to figure out what dl is. In this case, we're just moving in a straight line to the right. So dl is easy. Well, the distance that you move is an infinitesimal, so we'll call it dx. And we're moving to the right, so it's I hat. That's easy. dl just is I hat. Okay. So now we can compute the work. Oh, you're right. I'm so sorry. Minus f sine theta. There we go. So we have an integral. We're integrating from xa to xb. Let's call that xa and xb because they're different positions on the horizontal axis. And we integrate f cosine of theta minus f sub k, put a bracket around that I hat, plus n minus fg minus f sine theta, j hat, dotted into dx I hat. Now, the important part is that j hat dotted into I hat is 0. So this term goes away. All we're left with is this term. We're just left with an integral from xa to xb of f cosine theta minus f sub k dx, because I hat dot I hat is 1. Now these are constant, so we can pull them out. So we get f cosine of theta minus f sub k times an integral of xa to xb of dx. We know that the integral of dx is just the change in x. It's just xb minus xa, which we call delta x. So this is f cosine theta minus f sub k delta x. And that's the work done. So if you knew what the initial speed was, for example, you could figure out what the final speed is. Easy peasy. This was a simple example, though, because the forces were constant and because we traveled in a straight line. Things can get more complicated. So just as a quick remark, so for example, if we had wanted to find the final velocity in this problem, it would have been kind of involved. We would have had to know that we would have known the forces, or we would have had to find all the forces. We would have had to, should we write down everything like this in homework? Yeah, probably. Yep, you'd have to find all the forces. You'd have to find the acceleration in any given direction. Then you'd have to integrate that acceleration. Then you'd have to use that integral to find the change in the velocity, and then you could figure out the change in velocity. But this is a lot easier. In fact, we didn't even need to know anything about the vertical components of the forces. We only needed the horizontal components of the forces. And then it's just relatively straightforward. Like it's not that involved. You don't have to find acceleration and then integrate it. You're just integrating some force function. So you can simplify problems a lot with this method using the work energy theorem. The downside is you learn nothing about the direction of motion. You also learn nothing about how long this motion took to happen. All you learn is about the difference between the initial conditions and the final conditions. So there's a trade-off here. You won't always want to use the work energy theorem because sometimes you need to know more info. But there are situations where this is enough to solve a problem that you're interested in. Right. So already we're seeing that some forces just didn't contribute, right? We saw that the normal force and the gravitational force, neither of them contributed to the work done. So everything forces was constant and we moved it out of the integral. Yeah. So in fact, it turns out that you can kind of break this down even further by just talking about the work that is contributed to, or the contribution to the work done by individual forces. So for a given force, we can figure out how much work it does between 2 points. So recognize that the net force, if there's a whole bunch of forces on the object, it's just the sum of all of the actual forces, right? So what we can do is we can write the total work as a sum of individual works. I'm going to abbreviate this or subscript it total, the total work from A to B is an integral from a to b of f net dot dl, but we can break down what f net is. It's f1 plus f2 plus f3 plus dot dl. We can distribute the dot product and break up the integral. A to b of f1 dot dl plus an integral from a to b of f2 dot dl. I'm not actually going to do the third one, but you can see where I'm going with this. And so we actually just label that. We can label each of these, the work done, by the corresponding force. So we could, it actually makes sense to say how much work was done by the gravitational force, how much work was done by the pushing force, how much work was done by the frictional force, and so on. And so what we learn is if, for example, a particular force is always perpendicular to the hold on. Particular force is always perpendicular to the path, or to the motion rather, because the motion is along the path, then that means that, say, Fi, where I is whichever force it is, dot dl is 0 because the force is perpendicular to dl. And what that implies is it implies that for that particular force, that the work that it does is 0. And so that means that if you can figure out before you figure out the net force, if you can determine that some forces are always going to be perpendicular to the motion, for example, looking in this picture, the normal force is always up, but the motion is to the right. So we knew ahead of time that the force or the work done by the normal force is 0. Similarly, we knew ahead of time that the work done by the gravitational force is also 0 because gravity always points down and the path was always moving to the right. If you know ahead of time, you can just leave out those forces and those works and just compute the work done for the forces that you care about. So there's a relatively easy way to see why this is helpful. So let's look at a complicated system, a block sliding in a frictionless loop-de-loop. Frictionless loop-de-loop. Okay. Motion is the direction of velocity, yeah. So you have, this is always hard to draw. One more time. And then you have a loop-de-loop at the bottom, right? You have a block starting off over here. It's going to slide down. It's frictionless. There's gravity and so on and so forth. Maybe it starts off at some height and at some height here. And at a later date, it'll be over here, or at a later time, it'll be over here. It'll be moving up, whatever. It's sliding along, doing its thing, going around the loop-de-loop and so on. So at various points along the path, the forces get complicated, right? Like the normal force is always perpendicular. So the normal force when it's upside down is going to be in the same direction as the gravitational force, but then there will be centripetal accelerations. So the net acceleration might not be what you think it is. And the forces are always changing directions and it gets complicated. In particular, it's the normal force that gets complicated here because the normal force is always changing directions as the object changes directions. But the normal force is always perpendicular to the velocity because the object is sliding along the path, but the normal force is always perpendicular to the path. And so what that means is that the normal force is perpendicular to, okay, normal force is perpendicular. Okay. Normal force is always perpendicular to the path length vector. And that means that the work done by the normal force is 0, always, for this entire path, regardless of where it is on the path. The work done, or the normal force, doesn't do any work. So the total work done by the system which is an integral from a to b of, it'd be the normal force, which is a vector, minus, say, mg in the j hat direction, dot dl, we can just ignore that vector. We can just ignore it because it's always going to give us a dot product of 0. So this would just be, factoring out the minus mg, this would be minus mg, an integral from a to b of j hat dot dl. And now this is a lot easier to handle. You don't have a normal force always changing directions. You don't have to integrate along the entire path because this is a lot easier. This is a lot simpler of an integral to do. Now there is still some difficulty. What is this thing? What is an integral of j dot dl from a to b? Well, it turns out through some mathematical magic, it turns out to be the vertical displacement. Yeah, it's the displacement in the vertical direction, which we'll call delta y. So the end result is that the work done, the total work done between A and B from all of the forces in that situation, the normal force and the gravitational force, is just minus mg delta y. I'm not going to put a box around it because you might think that that means that that's always true. But in this case, the total work done is a really simple formula, right? If this distance here is delta y, stick a negative sign in front, multiply it by mg, and you get the work done. And then that means if you knew the initial velocity, you can find the final velocity easily, even though there are a whole bunch of complicated forces as the object swings around, goes around a loop, and so on and so forth. So this was very specific to this problem, that delta y is only showed up because of this particular problem. So I'm going to go into some detail, and then we'll have to continue it on Monday. So going to give a header. Gravity is conservative. Work doesn't have a direction, by the way. Work is just a number. So asking if there's a work in a direction, not really the right question to ask. Okay, so I said that there's mathematical magic to get there. So why is it that an integral from a to b of j dot dl is equal to delta y? Like how does that work? So think back to what you know about dot products. J dot dl is the projection of dl in the j direction. In the vertical direction. That's what the dot product means. So in particular, let's say that let's say that dl pointed up and to the left. And I'm going to draw a vertical line just as a reference. It's called this angle theta. And dl is going to be changing. Like this angle is going to be changing over time. And sometimes it'll point the other direction and so on. But importantly, the point is that j dot dl is just dl times cosine of theta, right? Where theta is the angle that dl makes with the vertical. So what we can say then, come on. What we can say then is that the integral from a to b of j dot dl is dl1, or they all have length dl. It's dl cosine 1 plus dl cosine 2, cosine theta 2, plus dl cosine theta 3, plus so on and so forth, where you're adding up all of the little angles, or where you're adding up the cosines of all the little angles as you go around your path. So that is, this is just the height. This is just the change in height, change in vertical position at position 1. This is the change in vertical position at position 2. And so on. So each of these little infinitesimal things that we're adding up, that's just the change in height over that path. So not divided by like a lot as the object travels along that path, its height is going to change. It's that change in height. So we're adding up all of the little changes in height, up, down, until we get to the end. And so the end result that we get is we get the change in height, the net change in height from the initial position to the final position. And so we end up with that this equals delta y. That's how we got that result. And it's because the integral is just j dot dl. It didn't have to be. It could have been something more complicated, and then we wouldn't have gotten delta y, but it did work out. So there's a remarkable feature. Oh, we're done. So I'm going to finish this up. And actually, yeah, I'll just actually end it here then. And I'll leave you on a cliffhanger. There is a remarkable feature, but we'll talk about it next time on Physics 9A.